So I've got a couple of relatively quick fire questions. To do at the end. So I'm just going to do this bit up the top on selection rules. Remind you what the atomic selection rules are. So a level which is triplet D10. So I think before we get on to the rest of the question, where have I got to going around the room? Somewhere in the semi-lap row. I haven't done just each row. Shall I start? Start with you. Sorry, am I not on? Right? No, I'm not
on. You're right. Is that better? Can you hear me better at the back? Who was the last person to answer a question this morning? Somewhere at the back there. I think it was the lady in blue. In which case we'll go to student next to Jasmeet. Sorry, I forgot your name. Yep. Do you know what the 3 up here on the triplet D0 means? Bit louder.
Sorry? Spin is 1, that's right. So that means S equals 1.
Jasmeet, what does D mean?
D is corresponds to L.
Yep.
Equals 2, right? What's the subscript?
J.
J, yep. Okay, you get the easy one. What's this O mean up here?
Top O.
Yeah.
That is parity.
That's parity, it says on parity, okay? So that's what that term means.
And the question is, which of these transitions are allowed? And I'm going to go around the room and ask you, but before we do that, what's the who's next one in? Lady.
What is the parity of these states?
For S it is even.
So,
D even.
they're all even.
For D it's odd.
No. All these states are even because there's no overlap.
Okay.
So little p it's odd. You're right. Capital P
may mean multiple states. It can still be even. So for a single p orbital, it's always odd. You're right. But if you have a capital letter, it can be the amalgamation of several states, and it can still be even though normally it's even because there's more than one odd in there. So these are all even. So the Laporte rule, if you remember, was you have to go from even to odd. So we know already before we start that everything here satisfies the Laporte rule. Okay? So coming forward, the next row, if we go to the triplet S1.
An allowed transition. Yep, you.
Hello.
So my favourite selection rule.
Come on, delta J equals, recite. What's delta J equals? Plus or minus 1 or 0. Sorry, which one I'm doing? Yeah, this one. Which one we were doing?
Sorry, so that's all right. Sorry, start again. It is, I'm getting the wrong selection rule here.
Yeah.
So this is L equals 2. What's L in this case? This is L equals 0. So the delta L selection rule is also 0 plus or minus 1. So this is forbidden. This is a strong selection rule. That is only that's a weak one. So this is a quite forbidden
transition, which means it actually happens, but it's not an allowed transition. Okay, moving along. So this is allowed, this was forbidden. Triplet P2, where are we in the, yes, it's you.
This is allowed, yeah. Sorry, this also has delta
S equals 1 as well. So this is a spin forbidden as well. But this one is allowed because delta S is 0, delta L is 1, delta J is 1. So they're all allowed. Singlet P1, where are we? Gentleman here. Yep. Singlet P1.
So it's delta S is equal to not zeros, not equal to 0, so it's not allowed.
So delta S is 1.
Yep. Yep. And yeah, so it's an intercombination line, exactly. So if you're doing this, the question actually says not which is forbidden and which is allowed, but I think you meant to put them in order. Yeah, give a probable order. So the triplet S1 and the singlet, sorry, triplet P2 should both, no, sorry, that's not allowed. That has delta L equals 2. So that was forbidden as well. So I got carried away here. So actually the order is, this one is allowed. So the strongest will be triplet P2. The next strongest will be the intercombination line, triplet P1. After that, it's triplet S1 because that's only, this has delta S not equal 0. This has delta L equals 2. So that's a forbidden transition. And then the weakest one will be this one because it's singlet delta. So it's got delta L equals 2 and it's got delta S not equal 0. So that's got two things wrong with it. So they can all actually occur, but this will be weak. And none of them actually violate either the Laporte rule or the delta J rule, which would mean they wouldn't happen at all on the dipole rule. But they go in that order in terms of strength. Okay. I got 2 of these because I wanted a lot of people to have a go at it, so I'll just get the next. Sorry? That's meant to be 0. Delta S is.
Sorry, I did not sound your comment, Bobby.
Delta L.
Delta L. Oh, I see. Delta L. Yeah, delta L equals 0 is all right. So, sorry, this is a. I'm talking rubbish. This is delta J.
Yeah.
So that's not a dipole allowed transition. That would have to be a quadrupole transition. And
It's a spin forbidden quadrupole transition, so it's incredibly weak. So the reality is, if you're in this state, maybe only 1 in 100 million photons will go into this state, so it's almost irrelevant. Yep, so as I said, I have 1 more of these to try.
so
I'm not going to do this bit here because we did quite a lot of that yesterday. In particular, I think we did a 3D5, no, we did 3D squared actually, but 3D5P, it's quite a lot of ink. And I think you know how to do it. But just to give you some context, so in the exam question we had, you were forming this 3D pi square by radiated recombination. And we talked about recombination lines, actually very high N but in these heavy atoms, you can also get them in low end states. It's called dielectronic recombination, and the guy I share football tickets with, Peter Story, actually discovered this process with his postdoc supervisor. One of the states formed would then be this triplet p odd state. So you can see it's odd here because there you've got two configurations. That one's even, that one's odd. That's going to be an odd configuration. So here we have is S equals 1, L equals 1, J equals 2, and it's odd. And again, no. So next question, where have we got to in the list? You've done one, is it your turn? Your turn, okay. Transition to triplet P1 odd.
Yep, absolutely. So no dipoles. Because of the Laporte
Rule. Actually, it's a completely allowed magnetic transition. So magnetic transitions have the strongest within the same configuration, and they have an alternative Laporte rule. They change the parities change the same. So that one is magnetic, but as we discussed, magnetic is very weak. So next one, singlet P1.
Delta S, you say? Yeah.
So this is a spin changing transition. How about the other things? They're all okay?
Even and out, so
Yeah, even and odd, yeah, that's fine.
like these ones. So
Yeah, delta J is 1, so that's fine. Delta L is 0, so all the others are fine. So this is an intercombination line. Okay, ladies. Triplet S1 from triplet P2 odd. It's allowed, absolutely. So it's delta S0, delta L1, delta J1, even odd, so that's all right.
Last transition.
We'll turn triplet F3 from triplet P2 odd. How about L? So what's
Do you know what L is for F?
Do you know what F? So it goes SPDF 0, 1, 2, 3. So L equals 3 here.
And
L equals 1 there. So we've got delta
L is 2. And that's not allowed. So this is a forbidden, that's in the jargon, that's a forbidden transition. So we've got singlet P1, sorry, triplet S1 is allowed. Singlet P1 is an intercombination line, that's an X strong. Triplet F3 is a forbidden transition. And then finally we've got triplet P1 odd, which is a magnetic transition, will be the weakest. So that's the batting order. Okay. So I was going to do, if people are all happy with that, I'm going to change subjects and look at quantum defects a bit, because I realized that I told you a bit about quantum defect theory, and I told you it was all great, but we haven't had any chance to practice it at all. So I thought I'd do a quantum defect question.
Okay, so there are two bits to this question on quantum defects.
So the first bit is just a bit of bookwork. So we've got triply ionized carbon, and in the triply ionized carbon has 6 electrons, so when you knock 6 electrons off, you get 3 electrons. So very often the atomic physicists call this lithium-like carbon because it has 3 electrons. Basically has the same electronic structure as lithium, but all the energy levels are spread out because of the Coulomb charge. And I will talk, when I talk about XML, I'll talk about doing molecular capacities, but when I first arrived at UCL, Mike Seaton was running something called atomic capacities. And they actually did isoelectronic sequences. So they do lithium-like everything from, they didn't do neutrals, so they do lithium-like boron, right the way up to lithium-like, I don't know, iron, and certainly beyond nickel. So maybe do 20 atoms, all with 3 electrons. And someone else would do boron-like with 4 electrons and so on. And they all had similar structures. So this then has a rather simple electronic structure. It's basically a closed shell 1s squared, which we could just forget about for the whole rest of the question, and then a 2s electron. And it takes a lot of energy to ionize it. And that's normal because when it takes you, I normally think in EV, in electron volts, it typically takes you of order of magnitude 10 EV to reduce the first electron. Then it takes you much more because you've already got a charge to pull off the second one, so maybe 20 EV and so on. 1 EV is about 8,000 wave numbers, so this is about 80 EV to take off the 4th electron. So given these 2 energy levels, what I'm asking you to do is estimate the energy doing the first one, but what you're actually asked to do here first is to give an expression of the energy levels in terms of R infinity and the content defect. So ENL equals R infinity minus 1 upon N minus mu NL squared, where mu NL is the quantum defect. And if you remember, the big property of quantum defects is that they vary very little with n. So the whole premise of this question is you assume they don't change with n. And we're doing everything with S states, so the fact they do change a lot with L doesn't matter, because you don't need that for your question. So what you need to work out is what the quantum defect is for this state, when you've got n equals 2, and then for this state when you've got n equals 3, and guesstimate, therefore, what the energy of n equals 4 would be using this formula. So see if you can have a go at that.
Sorry, I've left a very important bit out of that formula. Apologies. raised to the square root of effective charge. You get completely screwed up. So I think just to make sure you're on the right track, what do people think the effect? No, it's not 3. No, it's not 6. You bracketed the right answer, so you've got 2 possibilities in between. So you have, what you've got here is you have a core, and you have an extra electron. No, so if you have a neutral atom, the effective charge is 1. But here we've got a 3-fold ionized atom. So the net electron of the effective here, you have a charge of 6 originally for carbon, you have 2 core electrons, which cancel it, so that gives you Z effective is 4. So core is the nucleus plus the core electron. So this outer electron exists in effective charge of 4. And I have to say, having taught this for many years, that point always confuses everyone. So it's 1 more than you think it's going to be. So when you have a neutron, it has an effective charge of 1, and there's no charge of 3. Because you take 1 electron out. Yeah, that's four. Rises and yeah, so you have to evaluate that. No, I think we've got so if you guess the value of this board, you get a easily it may not be urgent, but you should evaluate it. So you're sort of making solve that question, solve that question, get value. That's not so try solving just that question. You get two simple numbers. So value of well, I can't only give you something good. Should be enough for estimate. So that's why you should do it separately. So it's usually the same number. Is so the student you have the question, you don't need to. Yeah. No, that's also
Sorry, can I comment? Because a couple of people are trying to get one answer when you should be getting two answers. So for the level with n equals 2 and this number, you can get a quantum defect. For the level with n equals 3 and this ionization potential, you can also get a quantum defect. Some people have managed to combine the two equations and trying to get one number. And that's not the point. The point is that you should get two different quantum defects. They may be quite similar. I don't have the model answer here and I haven't worked it out, but I'll wait till someone tells me. They may be quite similar, but you should not assume they're the same. In other words, you shouldn't be doing two equations which equate, assume they're the same. So you solve you solve this equation for this state, and then you solve the same equation for this state, and both of them will give you, one will give you mu30 and one will give you mu20. Okay? So you should be getting two separate quantum defects.
Yeah, okay, they look, I mean, they look, so in which case, you then need to, what do you assume the quantity for n equals 4 is? You have to, what you're meant to do now is to say, well, n equals 4, just do this. Oh, sorry, for n equals 4, what would the quantum defect be? Yeah, so you had 20 is that number, 30 is that number, the 40 would be, give me an estimate. It does put that in the formula. That should give you our best analysis. Okay. No, it's R-infinity times z squared divided by n minus u squared. So it's basically written in formula, the only difference is yeah, so it's yeah. Sorry, I should have given you R-infinity. Good question. Sorry, I'm just going to move this slide. Well, okay, I'll write it on there. The question actually had R-infinity in it, but it's off the top. What the value is. So, $108, no, 109. 677.58. So that's minus 1. So I write that again more neatly. 109.677.58. So that's minus 1. And that makes, if you take the ratio of R infinity to E, makes everything dimensionless. So both in way down the certain quantum defect, as you probably gathered, is just the number. So that goes to your dimensionality. That's right. So that's the effective quantum. I think it was the quantum defect. Sorry, 1 point. That seems a bit different. 4 answers here, and they're all radically different. I'm not sure. So if you think you've got the right answer, the criteria is quantum defect for n equals 2 and n equals 3 should be quite similar. So if they're differing by a half or something like that, you've not got the right answer. Okay? So they should be reasonably similar to each other. So I've got about 4 people who give me answers, and no 2 of them have agreed yet. And unfortunately, I don't have a model answer, but today's got me. I was hoping enough people get the same answer, but I know what the answer is. Okay, that's 3 to maybe 2 questions, and that's it. Don't get carried around decimal places. It's not precisely what the others are getting, but it's very close to what the others are getting, so I think that's the right one. These are only 3-digit numbers, so that's not the final answer. The final answer is the energy levels for ionization. Okay. Yeah, all right. You've done this to 3 figures, you're not going to get that. So 8, but yes. So 1, 1, 1, 0. Goes energy, ionization energy. Don't throw away your final answer. That may be right. That's not right. That's 0.15. Okay. That's not you can assume. Yeah, they want to assume it. Two values of okay, yeah, but it's assumed it's you go 2, 3, 4. So probably it's going to be slightly, you're going down and 1 from 2 is moving from 1 from 3. So probably 1 from 4 will be slightly smaller. I mean, to be honest, all of those are the same. They're not wrong. But probably the most accurate is this. So that was 158, so it's 156. Yeah, that's an approximate. It's an estimate. Okay, should we wrap this one up? So after a little bit of a battle, we did get consensus on what quantum defects were. So for this level, for n equals 2, people seem to jump and find out. 0.163. Sorry, I've not switched on. Thank you.
So if n equals 2 states, the quantum defect was generally 0.163, which to be honest for me is quite small for an S quantum number. They're normally more like 1. But obviously this is presumably the right answer, and I assume what happens is because you've got a highly ionized core, the 1s orbital is very tightly bound and you don't penetrate very much into it. And then for this one, people got 0.158. And then you were meant to estimate, so this is N20, this is N30, and you're meant to estimate N40. And I would say that it's going to be some number slightly less than 0.158 on the grounds you've got a series here. So 0.1, any estimate between 0.158 to say 0.156 or even 1.4 is probably a reasonable estimate. So you get a variety of slightly different answers for the ionization energy, which was, I know, 11.0. Someone give me a number. You got a number? What was your ionization energy? 11897. And what effective quantum number, what quantum defect did you use for n equals 4? What quantum defect did you use for n equals 4? For n equals 4, what quantum defect? So if you use 1.7, you get that. If you use a slightly smaller quantum defect, you get a slightly higher energy. So it's something in that ballpark. This is an estimate method. There's no precise answer. Anything in this region would be considered a reasonable answer. Okay, so people happy with that as a procedure? Yep. Have I got a digit too little? Yes. Yeah, should be 6 digits. You missed me a digit. 1 1.
118959.
8959.
Yeah? Okay, that's one more digit. Thank you. Any more comments on this? So that was all I actually prepared, because I was rather hoping people would suggest some things they wanted to go on. I can keep on giving you random questions if you want, or you can have another try at saying what topic you would like a question on. Right, okay. Does K218b have life? Discuss. I don't think I have your exam tomorrow is going to be multiple choice questions. I don't think I have a good multiple choice problem for an exoplanet. Just thinking. So actually, I taught this course before anyone had done any exoplanet characterizations. At the point when I taught this course, there was no spectroscopy of exoplanets, so it didn't appear in it. But I just tried to think whether there's an easy question one could ask about that. Not off the top of my head. I can ask lots of qualitative questions, but they're not quite the same. Any other thoughts on what we may want to? Yep.
Resonances, study of resonances in electronic excitation.
So, first thing to say is that the word resonance,
which Jasmeet and I use a lot together, has a one meaning in electron collisions and has a completely different meaning in spectroscopy. So a resonance in spectroscopy is when you get two energy levels which by coincidence are very close to each other and interact. In electron collisions it means something else, and I'm not going to tell you what because I think I'll just muddy the water. Many years ago I went to a meeting organised by the Institute of Physics between collision physicists and condensed matter physicists on the subject of resonances, and it became apparent that the two halves of the community had a completely different definition of what a resonance was and spent the whole afternoon talking about completely different problems, and there was no meeting in mind whatsoever. So it's a rather loaded word, and I have to say I think the spectroscopers have the right meaning opposed to the electron collision people, because a resonance really is when two states are in resonance. And when you get people happy if I clear this? Yep, okay. That looks like a blank piece of paper. Oh, it doesn't work like that, does it? I just go on one of these and go to the end and scribble on it, probably. So if you have, say, electronic states with vibrational levels in, you have two of them quite close to each other, and I should use a different color for that, so I'm going to start again. You have an electronic state with vibrational levels in, and then you have another electronic state with vibrational levels in, and then they have sublevels which depend on J. So we need, don't do that to me. We need the sublevels here depend on J. And sublevels here depend on J. And if they have the same J and parity, they can then interact. And what happens is that they actually push each other apart. So you get energy as a function of J. Which will go, sorry, I need to get this right. Will go something like this. They actually, they perturb each, instead of having a nice smooth theory, they interact and they push each other apart. And this becomes a matrix problem where you have some interaction here. Like that, you have to solve the problem and they push each other apart by the amount of the interaction. So that's quite a standard resonance thing. When I talked about the misassignment of calcium oxide, it was entirely due to this. That they got the resonances all wrong, they got the mechanism all wrong, which meant they were coupling the wrong states, and they got all the labels all messed up. And it's quite subtle and quite difficult. So that's resonance interaction. It's very common in electronically excited states. It's not so common in ground states. And for diatomics, you get something called the non-crossing rule. So I've drawn those two potentials like this, because if they cross each other, and we saw lots of pictures today, actually earlier, of potentials that cross. And that's fine if they have different symmetries. But if these, for instance, both happen to be singlet sigma plus, then actually you don't behave like this. You behave like this. So you get one state which does that. And you get another state that does that. They don't cross each other. So you get funny states with funny shape on them. And I referred to the hydrogen having this EF state. it was caused by this non-crossing. And I have a new postdoc, Ryan Brady, who actually, his whole thesis, we called him the spaghetti unscrambler. His whole thesis was actually on how to sort out these non-crossing and put in the non-adiabatic couplings. And he even did it actually for some resonance curves as well, just with Jan Schneider. Because there's quite a lot of physics actually in what's going on here and trying to get it right. So that's going off topic and won't be on the exam tomorrow. But I could witter for hours on molecular physics problems if you want, but they won't be relevant to your exam revision. Anything else you understand? It was all perfectly clear, and you want to go and get wet in the thunderstorm. I've put an awful lot of information past you in a relatively short time, so I'll be a bit surprised if you manage to absorb it all perfectly. Yep. Yeah, I think
Looking at the
I got an email today. I'm now a fully fledged member of Jan or whatever it is, and I got their newsletter today for the first time. And their newsletter seemed to have a list of conferences and archives. So I think that Jan will ask for all my presentations to be put on an archive somewhere. That's what I'm expecting. Bobby hasn't said that to me, but I think I should do it because they're on this memory stick, so I can give them to him here now. And I think they will go somewhere on an archive, and maybe he can circulate them around anyway beforehand. So yeah, I'm quite happy for you to have them all if you want to go back and look at them as a record. And on a related topic, I'm told that if you're all here tomorrow, you get your certificate. It doesn't matter what you do in the exam. I assume you'll also at some point get told your exam mark. Your certificate is a long service award that you managed to last the whole week, and you're still here. And it's not a pass-fail on what you do on the exam, but I assume you will also get a mark on your exam.
Any prize for the first one?
That's not a question for me. It's a good question, but it's not a question for me. I think that
you have to ask Bobby Anthony. I don't know what the Jan rules are. I'm actually, that's tomorrow, we have our MSc exam board.
And there's a big argument going on because we have 5 MSCs
and only 3 prizes. That doesn't match very well. I'm seeing some rather interesting emails also. So tomorrow is the 31st of October, which in Christian cultures is Halloween. That's right. So when I wrote the exam, it had a subtitle saying Jonathan's Halloween horror story. You can tell me tomorrow whether that's been deleted from the official exam that you get, but that was what it was titled. I nearly put trick or treat because it's trick or treat. And the questions are deliberately quite varied, so there should be some that everyone finds reasonably easy. There are some that are deliberately quite difficult, and not only they're difficult, you have to spend quite a lot of time doing them. And that's on purpose because I try to spread things out a bit. So they should find some you should say, oh, that's obvious, and tick it down, and you'll sit there scratching your head and having to do some maths to get an answer. And that's by design. Yes, and I asked that question because there was one question you can't do without a calculator. So before I put it down, I said to Bobby, okay, we can use it, yeah, that's fine. Okay. In which case I might wrap up and I'll talk to you about XML tomorrow morning, bright and early. What time do we have? Just remind myself what the schedule is tomorrow. It's different. So tomorrow we've got a lecture. You'll be out of bed. It's at 9:30.
So no, it's lying in bed till 10:30 we've had for the last 2 days. And then after chai, no chai. You go straight into your exam. No artificial stimulants. So you get chai after your exam, and then there's a closing ceremony after chai. Okay. So that's the schedule tomorrow. So lecture at 9:30, which will just be on the XML project, which I can't think of any questions on, apart from you can do a new molecular line list and calculate 10 billion lines for me, but not with your calculator. Okay, so I'll see you all tomorrow, bright and early. Okay.